How's everybody? Last day of class. Well, one person's good. Good job, Christian. Last day of class is a week from tomorrow. Can you believe that? Final is a week from Saturday. Yeah. And we haven't even started today we start the last 4 sections. So I apologize. I know I sent this out in the email, but I wish I would have changed the schedule around so we had a few more days for review and tighten up a few places earlier in the semester. But, all right. Who'd like to start us off with a prayer? Thank you.
Our dear Heavenly Father, we're grateful for this opportunity that we have to study math today. We ask that our minds will be enlightened and that we may be able to feel comfortable asking any questions that we might have so that we can get the most out of this experience here at BYU. We say these things in the name of Jesus Christ. Amen.
Thanks. So you're working on the iClicker quiz. Exam starts today. So in the testing center. Last day is Friday. If you go in after 2, it'll cost you $5. So don't do that if you can help it. There's a review session. When's the review session today? 4 to 6. Review session today, 4 to 6 in what room?
173 at the town. 173 at the town.
Okay. So yeah, that's 170. Yes? It's 11:3. To 11:11. So it doesn't explicitly do 11:1 and 11:2, but some of that material will be on there because you have to find limits of sequences and when you're doing some tests, right? And like the test for divergence and the geometric series tests, those are fair game because 11:7, those are fair game on 11:7 when you're testing. So okay. Other questions? Okay. I would encourage you to start planning out times to review for the final right now. Like reviewing for this exam will be good because you'll have a week and a half later you'll be taking an exam and a lot of the material that you're reviewing for now will be on that final exam. But the stuff earlier from the semester and the stuff that you'll be working on over the next week it's going to be new. Make sure you focus on, it's going to either be new or it's going to be forgotten. So make sure you go back and study those things. So, okay. Who needs more time on this problem? Snap if you need more time. Okay. No, I'd prefer you don't. So, thanks. Okay, take 30 more seconds. Well, let me just do some general explanation about parametric curves while you're working on this. So, there's a lot of advantages of parametric curves. When you have curves that aren't functions of just x, okay, like paths of objects, kind of crazy paths of objects, you might be able to easily write those down in a parametric form, whereas just talking about x and y or x, y, and z, it might not be a thing. So we can use parameterized curves. So think anytime you have something that's tracing out a path, parameterized curves are nice. So think of like a CNC mill, okay, or a 5-axis mill where you're carving things out. The parameterized curves come in really important. Anytime you're actually, a lot of the visual stuff and drawing, you're connected somehow to a parameterized curve. A lot of like paths in video games, or video game characters, or paths of planes or whatever you're doing, they're done with parametric form. They have a curve you want to follow, and at a certain time you want it to be on that curve in a certain way. So it can simplify things because you can break up the position or the quantities into separate components, like an x component, a y component, and a z component. Sometimes doing that, instead of trying to have y as a function of x, and thinking of x as a function of t, or x as a function of theta, and y as a function of t, or y as a function of theta, then you can actually get a much simpler form. And I'll talk about that later with an example. If we don't get to it today, we'll get to it on Friday. And the best part about parameterized curves. You can draw really cool pictures. So these are some generated in Wolfram Alpha or Mathematica. So there's a Cupid, Einstein, Abraham Lincoln, and that Korean singer. So, and like spirographs, you guys may or may not have had spirographs where you had the little gears with pins, and they had holes in them, and you put the pins in, and some you would hold still, and others you would move around. All of those can be modeled with parameterized curves, and they're real. And it's easier to actually make those on your. Might be easier to make those on your with a calculator than other things. So these were just a couple online. You can look for parameterized curves pictures or spirograph type pictures and find them online. This one actually gives the equations, so you can see that x and y are both given in terms of t. So your x coordinate is a function of time, even though y is not a function of x here. Right? If you tell me my x coordinate, I don't know exactly what my y coordinate is. Okay? There's too many y coordinates. But if you tell me a time, I'm only in one spot. My x coordinate only has one value at a given time. And my y coordinate only has one value at a given time. So even though y is not a function of x, meaning y isn't determined by x, the x coordinate and the y coordinate are determined by a given time. So you get some more flexibility here. It can add a little complexity because you're dealing with two equations instead of one, or three equations instead of one. So, okay. All right. So it is nice to be able to go back and forth between Cartesian coordinates and parameterized coordinates. Sometimes you're better able to make sense of it one way or the other. Okay? Even if you're able to, it's better to model it with a parameterized curve. You might want to know, or might tell you something because you're more familiar with the Cartesian coordinates to put it into Cartesian coordinates. So here's an example. So let's get these together. So one of the strategies, or the main strategy in combining these, is to solve for t and then substitute it in. That's one strategy. So that works really well when you have things like this. Okay, then what is this in terms of Cartesian coordinates? What would the graph be, or the relationship be? Well, I could take one of these, like the square root of t, and rewrite this as x squared of t, or even just x squared equals t. And now I can plug t back in over here, so I get y is equal to x squared cubed. So I get y equals x to the 6th. Okay, so that's one standard strategy, really nice and straightforward if it works that way. Sometimes it does not work as well. Like in this example, you can do it, but it's more complicated. The other strategy is use formulas. Okay, so I know a formula that allows sine and cosine to become a constant, right? So here I can solve, I'm not going to solve for t, but I'm going to solve for some function of t and use a formula that allows me to get rid of these things. So a sine squared plus a cosine squared I can replace with just a 1. So I'm going to solve for sine squared. So if x of t, let me just write x. If x equals 3 sine of t, then x thirds is sine of t. But I don't want sine of t. What do I want? Sine squared of t, so I can square both sides. And I can do a similar thing with y of t. Y of t is already cosine. Just write y. So y squared is cosine squared t. And now I can plug in cosine, whatever cosine squared is equals, I can plug that in here. Whatever sine squared equals, I can plug it in there. So cosine, So cosine is equal to y squared. Sine squared is equal to x, missed a square there, x over 3 quantity squared. And that whole thing equals 1. So what's that the equation of? An ellipse. So that's one way to do that problem. So the answer is so the correct answer was A, and the vast majority of you guys got that. And there's another way to do this. If you did the reading in the videos, you would have already seen examples where like y of t equals sine of t and x of t equals cosine of t. And you would have known that that traces a circle out this direction, a unit circle. But if you multiply the sine by 3 or one of these by 3, then what happens? Then you're starting not out here at 1, but you're starting out here at 3. And so then you end up with like this. Okay? So, look, another picture. It's a picture of an eye. So, okay. So that was another, some of you may have thought about it that way. So why does this trace out those curves? Like, why does this trace out this green curve? We can start, you can start in graphing by thinking about what is t, what is x of, what's my x coordinate at that time, and what is my y coordinate at that time. Oops. So you can say, well, at time equals 0, where am I? Where am I up here? Well, cosine of 0 is 1. Sine of 0 is 0, so I'm at 1, 0. Oh, I drew this the wrong way, didn't I? Dang. There you go. Okay, stretched in a different direction. So what about time equals pi fourths? Then cosine of pi fourths is square root of 2 over 2. And sine of pi fourths is also square root of 2 over 2, but I have to multiply that by 3. So I'm going to be so here's one. So here's pi fourths. So, well, pi fourths, I'm not thinking of that as an angle, I'm thinking of it as a time. So my next coordinate is going to be, if this is 1, my x coordinate is about 0.7, and then I go up 3.7s, which is about 2. So I'm about right there. So in that first little bit, I've come up to there. Then a pi halves. Cosine is 0. Sine is 1. So 3 times 1 is 3. So where have I ended up? Boy, I really need to do a lot of work on not making my pictures run into each other. So you can get a new point for every single time. You can just plug it in and it tells you what your coordinates are. Okay. Parameterized curves are they're the mathematician's etch-a-sketch, right? When you have an etch-a-sketch, you can control your x coordinate and your y coordinate with the two knobs, right? Independent of each other. You want your x to go up and down, you can do that. Y up and down, y back and forth, you can do that. Okay? And as you twist both of them, you can get that to go in different shapes. And you can trace out whatever you want. It doesn't have to be a function. The x coordinate doesn't have to be a function. The y coordinate doesn't have to be a function of the x coordinate. So that's what makes them so flexible and powerful. Okay. Any questions so far? All right. Okay, so suppose I throw an object up in the air. I throw it and I'll just do this. Goes 16 feet high. It's in the air for 2 seconds. How would you figure out how far that object traveled? What did you say? Arc length? Okay. Someone said integral, someone said arc length?
Well, if it was, can I assume that like halfway is 1 second, like halfway, like the pinnacle is 1 second?
Yep.
I would find out how long it takes to fall 9.8 feet, like how long it takes for it to fall to the ground using gravitational acceleration.
Okay, so use some physics. Okay. So all those are good ideas, but I actually haven't given you enough information to calculate how far this has traveled. What other information are you missing? You actually don't need the initial, well, if you knew the initial if you knew the initial speed and the initial angle, you don't know which direction I've thrown this thing. I could at minimum have thrown it straight up and it would have come straight down, but I could have thrown it across the room. Well, the ceiling isn't high enough here, but I could have thrown it for a long ways. So you don't know enough. On all the times that we've analyzed falling objects or thrown objects, we've only cared about the height. We haven't talked actually about the x-coordinate at all. To do that, you need to introduce something new. We can now do both of those with a parameterized curve. We can talk about where the height and the distance at the same time. So with the time t. So here it's like not enough info. But if I give you something like this, okay, and that is the height curve right there. But if I combine it with the x-coordinate, now we have a way of analyzing the path of that object, x-coordinate and y-coordinate, and where it is at any time. So and this is still x, and this is still y. And some of you are thinking, but Brother Corey, we've done XY graphs before. We have. But they haven't been connected to a time on where the position is. Where they haven't been connected to where the object is at any time t. So you couldn't answer questions like, how fast is it going in 1 second? Where is it at after 1 second? So how fast is the height increasing versus how fast is the x-coordinate increasing in 1 second? So I'm going to start filling out these tables. I want you guys, I gave you the parameterized curve. I want you guys to put this into Cartesian coordinates for me. Okay? Yes? Oh, you mean this? That's a plus sign. So I do try to put out tails on my t's. I didn't do a great job. So, plus. Right. Thanks. I used to write my t's and plus signs exactly the same, and it drove my students crazy. So I started to put little tails on my t's like that, but not enough tail. Thanks for asking about that. Yeah, thanks. All right. So I went ahead and started filling out a table. So at different times, I could figure out where the value, what the position was of the ball or whatever it was that I threw. So at time equals 0, I'm right there. Then time equals 1/2. Then time equals 1. Then time equals 3/2. Time equals 2. Okay. And then I eliminate the parameter by by solving in this equation for t, and I got t equals x over 17, and then wherever there was a t in this equation, I substituted in x over 17, and I get this, which you can simplify some, but we'll just keep it like that. Okay. Any questions? Yes. I didn't use this to help me graph. I could now graph this, and it would give me the same curve. But I lose some information here, right? That tells me, or it gives me different information. It says if you know the x-coordinate, how far away you are from the starting point, then you can know what your height is. But I missed that time component. I don't know now, like, where it is at any time on that path. I don't know how long it took me to get there. Like, I don't know what time it started, what time it ended. Like, none of that is in there. I just know, hey, this is the path. So I'm missing that time component of something actually traveling or drawing out that curve. So this is what we've been working with a lot, right? This is what you get. But if that x coordinate isn't your if our x axis isn't really a time axis, then we lose track of it's harder for us to talk about when things are happening, or when we want something to happen. Okay. Okay, I'm going to give you guys a couple coordinates. I want you to think about you can plot points, you can think about it any way you want, to think about what's the graph, like where it is and what's the shape on the coordinate plane. Maybe we should start with this one. I'll make that one number 2. Let me change that to the 3. Let's just do that much. All right. I know you guys haven't had enough time to do all of these, or at least all of you haven't had enough time to work through all of these. I put my work for number 1 up here. So we kind of already did number 1. I've got x is cosine, y is sine. So I'm going to use the Pythagorean identity, cosine squared plus sine squared equals 1. So I use the original equations, get the right side into cosine squared and sine squared respectively, and then I can replace those. So x squared takes the place of cosine squared, y squared takes the place of sine squared, and I just get x squared plus y squared equals 1. And that's the equation, that's the circle of radius 1 centered at 0, 0. Okay? Now, for number 2, I don't have to do a lot of work if I understand what's going on, if I'm a little clever. So, number 1 gives me all the hard work I need to do. So what's a slick way to think about number 2 that can help me out here? Okay, so one strategy, you can do x minus 1. So x minus 1 equals cosine of t, and then you do the same thing that we did above, and you'll end up with x minus 1 squared plus y squared of 1. And then remembering what your algebra is, you have a unit circle, but the center is now shifted to the right one, so you can figure it out that way. But there's actually even a slicker way. There's even a better way. I don't know if it's better, but it's a shorter way. Based off of what I'm doing, how I'm changing the one up there versus this one if I add that 1 to that x coordinate, to the x coordinates of those. How are all the x coordinates? If I go through and make an xy table at any time t, and I did that for both of these, how is this row of x's going to be different than that row of x's? It's going to be 1 higher. So that means I shifted all of my coordinates 1 more. I increased my x. So which way does that move things? Right. They're up by 1 more. So here I have the exact same circle. So that's a unit circle centered at 1, 0 instead of 0, 0. Because I just increased all my x coordinates from the one I had above by 1. So, okay? So there are 2 different ways of doing that. Okay, let's talk about 3. So, it might be easiest to start doing this. This was a strategy I was really comfortable with when I was in your shoes. So at time equals 0, what am I at? Cosine of 0 is 1, sine of 0 is 0. So I've got a graph here, and I'm at 1, 0. All right. What about pi halves? Cosine of 3 pi halves? Ooh. Cosine of 3 pi halves. Let me think about what cosine looks like here. So this is pi. This is, oops, that's 2 pi. This is pi. This is pi halves. So So 3 pi halves will be right here. 3 pi halves. So we're at 0 at 3 pi halves. What about sine of pi halves? 1. So now my next point is going to be up here. What about at pi? At pi, I'm at 1, 0. -1, thanks. There. Looks like we're getting a circle again. Right? That's what it looks like. I went from here, and I got to there, and then I got to there. But if you were to graph this on your calculator, you would not be getting a circle. What is going on here? Are you pointing to hit your neighbor? Yeah. So from the equation that we did earlier, from up here, and our understanding of sine, sine from 0 to pi halves goes from 0 to 1. Right, so from here, our y-coordinate, from here to there, it does go up. Right? Like the y-coordinate does go from 0 to 1 as it goes from 0 to pi halves. But what happens to cosine of 3t from 0 to pi halves? That makes cosine, that takes cosine from 0 to cosine of 3 pi halves. And that just doesn't go from 1 to 0. That goes from 1 back down to 0, back down to a -1, and then back up to 0. So I haven't picked t. I've picked t with too big of a jump to figure out really what's going on in that interval from 0 to pi halves. I have to pick some points that are I have to take smaller intervals on my t to figure out what's going on. Okay? So for example, what would be a good value to pick here? So pi thirds would be a nice one. Okay, because I'd have 3 cosine of 3 times pi thirds. So somewhere in here, so pi halves, so pi thirds. Cosine of pi thirds will be what? That's cosine of 3 pi thirds will be cosine of pi. Cosine of pi is a minus 1, right? And did I write this down the right way? Right, x of t is 3 of t. And then sine of pi thirds is what? Square root of 3 over 2. So, did I get that right? Why do I have a -1 and a -1? Yeah, so there are, we're okay, right? Yeah. Okay. Whew. All right. So by the time I ended up with, when I plugged in pi, I was right here. But when I plugged in pi thirds, actually my x-coordinate is still a -1, but what's my y-coordinate? Square root of 3 over 2, so I'm not yet up to here. I'm actually over, square root of 3 over 2 is, what points? Pretty high. It's up here. I'm right there. So what's going on? Well, I didn't move this way. I went like this way. And then I didn't come down there. I went back over here and back down to there. So we've got some craziness going on. If you don't sample close enough, you can't see what's going on in these curves. So one thing that's really helpful in situations like this is thinking about thinking about these curves and what they look like. So if you know something about how sine changes, then you can be thinking about, oh, my x-coordinate's going to be increasing here and get up to 1, or it's going to be decreasing here down to a -1. And that can help you reason through what's happening with the graphs. So some students find it helpful to write out, for in this example, like sine of t versus t graph and cosine of t versus t. So then you can start reasoning through what your different values are. Or maybe it would be better in this case to think to graph cosine of 3t versus t, and then you'd have something that would go, right, it's going to be something more like that. You have to figure out where your values are. So, okay, questions so far? Yes? To find what? Not a slick way that I know of. There might be. I haven't spent a lot of time thinking about it. Someone else asked that question when you guys were working, and yeah, I don't know. It's not you're not going to end up with anything nice to begin with, because we've done enough to know that it's not a function. You're not going to be able to solve it in y in terms of x, because it's not a function, right? So, and it's not, and x isn't a function of y. So whatever you get, it's going to be kind of crazy anyway. So, all right, the fun stuff with the parameterized curves comes with the calculus of that, and that's what we'll be focusing on next time. So good luck on your exam, you guys.